Good day, everyone. I am Krishna Kalimlim from Group 6, and today we're going to talk about writing proofs. In mathematics, writing proofs is an essential skill because it shows how and why a statement is true, not just that it is true. Proofs help us explain our reasoning clearly, our logical steps, and communicate ideas in a way that others can understand. They are the foundation of all mathematical knowledge, from simple equations to advanced equations. Writing proof is a logical and organized explanation that demonstrates the truth of a mathematical statement. It uses previously known facts, definitions, theorems, and logical reasoning to show step by step that a conclusion must be true. Writing a proof means presenting these steps clearly, accurately, and convincingly.
Every proof, regardless of its complexity, has three main parts. The first part is the setup or premises. You must clearly state what are you assuming is true. These are your hypotheses or premises. Example, if we prove P implies Q, we must assume P is true. Number two is the body or inference. This is the core of the proof. It's a list of logic steps. The golden rule, every new state must be supported by a justification. This justification must be definition as known theorem, a rule of inference. The last part is the conclusion. This was the step 3. The last statement in your sequence must be the conclusion. You are intended to prove when often use Q, E, D.
Rules of inference are logical patterns used to derive a conclusion from a set of premises. They form the basis of constructing valid arguments, ensuring that the premises are true. The conclusion must also be true. Examples of common rules include modus ponens, modus tollens, and hypothetical syllogism. How rules of inference work. Premises, the starting statement or assumption of an argument. Conclusions, the state that is derived from the premises. Valid arguments, an argument where the conclusion logically and necessarily follows the premises. Process, you start with a set of premises and apply a rule of inference to derive a new statement. This new statement can then also be used as a premise in the next step, and the process continues until the desired conclusion is reached. Modus ponens. If you have a statement, if P then Q, and you know that P is true, you can conclude that Q is also true. An example of this is if it's raining, which is P, then the ground is wet, which is Q. It is raining P, therefore the ground is wet, which is Q. Modus tollens. If P then Q and you know that Q is false, then you can conclude that P is also false. An example of this is if it's raining P, then the ground is wet, which is Q again. But if the ground is not wet, then it is not raining. Hypothetical syllogism. If you have P, then Q, and you have Q, you have R. You can conclude that if P, then R. An example of this is when I study hard, which is P, I will get good grades, which is Q. If I have good grades, which is Q, I will pass the class, which is R. Therefore, if I study hard, which is P, I will pass the class, which is R. Disjunctive syllogism. If you have a statement P or Q, and you know that P is false, you can conclude that Q is true. It's true. An example of this, I will eat pizza, which is P, or I will eat pasta, which is Q. I did not eat pizza, therefore I ate pasta, which is Q.
Okay, so the first of the three main proofs is the direct proof. And the goal here is to prove that P implies Q. So we assume P is true, and we use definitions, algebra, and rules of inference to show that P logically forces Q to be true. So an example here is, let's prove that if x is an even integer, then x squared is, well, also an even integer. So let's assume P. X is an even integer. By definition, this means that x equals 2k, as in 2 times 1, 2 times 2, 4, 2 times 3, 6. These are all even integers, so yeah, for some integer k. Now, we square both sides. X squared equals to the quantity 2k squared. And when you simplify this, we'll have x squared equals to 4k squared. Now let's factor out the number 2. So when we factor out 2, we'll be left with x squared equals to 2k, 2 times the quantity 2k squared. And since 2k squared, that quantity, is an integer, let's call it m, we have x squared equals to 2m. So in conclusion, or by definition, x squared is an even integer.
The equivalent reverse, proof by contraposition. Goal to prove P implies Q when a direct proof is too difficult. Instead of proving P implies Q, you prove it logically. Equivalent from the contrapositive. When negative P implies negative Q, assume negative Q is true. Assume the conclusion is false. Use a direct proof method to show that this leads to a negative P. Example, prove that if 3n plus 2 is odd, then n is odd. Assume negative Q, assume n is not odd. This means even. If n is even, n equals 2k for some integer k. Substitute this into the original expression. 3n plus 2 equals 3 2k plus 2. Simplify 3k plus 2 equals 6k plus 2 equals 2. Since 3k plus 1 is an integer, 3n plus 2 is a multiple of 2, which means it's even. Conclusion negative P, we have proven that 3n plus 2 is not odd. Since negative P implies negative Q, the original statement P implies Q is true.
Proof by contradiction is a method of mathematical reasoning where you assume the opposite of what you want to prove. Then, show that this assumption leads to a logical contradiction, meaning it cannot possibly be true, since the assumption produces an impossible or false outcome. The only remaining logical conclusion is the original statement must be true. Proof of contradiction. 1. Assume 2 is irrational. 2. If 2 is irrational, it can be written as a fraction. A, B, and lowest terms where A and B have no common factors. 3. Squaring both sides lead to the ultimate contradiction that an A must be both been even, which violates the initial assumption that they had no common factors. 4. Since the assumption leads to a contradiction, 2 must be irrational.
A mathematical proof is a logical and organized explanation that demonstrates the truth of a mathematical statement. It uses previously known facts, definitions, theorems, and logical reasoning to show step by step that a conclusion must be true. There are three parts of proof: the setup or premise, the body or inferences, and the conclusion. Inferences are like your proof building tools. They are universally accepted laws that allow you to deduce new truths from the old ones. There are three main proof: the direct proof, proof by contraposition, and proof by contradiction.